Now that we've set up the formula for u of ys, we could put a box around that and say we're done, but as good mathematicians, we want to simplify u of ys. And so our first step towards simplifying u of ys. Notice u of ys in that first centered equation on the second paragraph of this section on Fourier transform. It has two integrals in it and three exponential functions in it. So we're going to work on simplifying some of that. So here I'm going to show just what we do when it says exchanging the order of integration. Here's the formula that we have, u of ys equals. So again, this is our solution. We could put a box around it and we're done. It's just that it looks not as nice as we would like it to look. And so what we do is we are looking at and seeing there are two integrals here, and some pieces do not, like in the inside here, there are these two pieces actually, this exponential and g of zeta, and noticing that, xi, g of xi does not depend on omega, and so our first goal, especially since it's the unknown, like it's a given parameter anyway, our first goal is to take that outside the integral with respect to omega. And so when we change the order of integration, notice this is going from dxi to d omega. This now is omega going from minus infinity to infinity. This one is zeta xi going from minus infinity to infinity. That's different from the other way around. Remember, the inside one is always the first integral. The outside is always the outside integral. And so when we switch the order and put d omega on the inside and d xi on the outside, we can take something that depends only on xi and put it there. So now inside, what's left inside is everything that depends on omega then has to go inside the integral with respect to omega. And so the e to the minus omega squared s has to stay inside that inner integral, the one with respect to omega. E to the I omega y has to move to the inside. And so notice we have that right here. We've combined the two e to the I omega factors by adding the exponents. And we have the common I omega, and so there's a positive y and a minus zeta. And so this is now what we are integrating first, our inside integral as we work from the inside out. Notice this integral is an integral with respect to omega that we can do. It's just exponentials. There's no unknown function g. And so our next step is going to be to do this integral. Not the easiest integral you guys have ever done, but we will do it. And it's very cool, a very cool integral in the next video. But just so we can see, again, keep track of where all this is going, if we do that integral, we can call that big U. And notice that time shows up as s, but now the space variable is y minus xi. We don't have y by itself, we don't have xi by itself, we have y minus xi. What type of integral is this? This is a convolution integral. We can say u is g star big U, where big U is what we get when we do this integral. So notice also this integral, since it's e to the positive I omega space, and there is a 1 over 2 pi, this is itself an inverse Fourier transform. So to do this inverse Fourier transform, remember, we started with just u hat equals, and we did the inverse Fourier transform to get all this, but the work of the inverse Fourier transform is actually to do this inverse Fourier transform. That will be the next video. The final result, though, skipping ahead just so you can see where this is all going, is the final result is that U ends up being a convolution from the given G, which has everything to do with the initial condition and nothing to do with the PDE itself. But then there's U here, and notice U only comes from the structure of the PDE itself. There's no G involved. There's no initial condition involved. So there's the initial condition convolved with what we call the heat kernel. We'll get to that by the end of this page.